Alright, Assalamualaikum everyone. Okay, so we're gonna start our online lecture. So what I'm gonna do is I'm gonna record all this lecturing here, and I'm gonna upload on YouTube, and then I'm gonna link the YouTube to goals so that you all can view from goals as well. Okay. Alright. So before we start, let's refresh what we did last week. Okay, so last week what we did is we had a look into this Rn here. Okay, so as you know, we have R2, R3, R4, and this number here can go up to any number. So we did note that as Rn, alright? And then we have this, we have the definition here, definitions of vector addition and scalar multiplication in Rn. So we had a look at this one here. So this is the addition, and this is the scalar multiplication. Okay, so what else we did last week? We had a look at the some examples here. Example on how you calculate u plus v, 2u, and also v minus 2u. These are examples that we had a look last week. Okay, and then we have this theorem 4.2 here. This is the theorem that explains the properties of vector addition and scalar multiplication in Rn. So you have all of these here. There are 10 properties altogether. All right. And then we also had a look at this example here in R4. So we did this all, we have done this calculation here on the whiteboard if you still remember. And then we had a look at part B example as well. And then what else? Okay, so we had a look at our theorem 4.3. This is the properties of additive inverse and also additive identity and also additive inverse. So additive identity is basically 0, and additive inverse is basically the negative of that particular vector you are working with, right? So you have these 6 properties here. And then, okay, so what else we did is we proved, I think 2 of the properties. The first properties that we prove is v plus u is equals to v, which is the first one. Okay, which implies that u is equals to 0. And the second property that we proved last week on the whiteboard is this one here, where you have v plus u equals to 0 implies that u is equals to negative v. Alright, and then what else we did? Okay, so we had a look at linear combination of vectors. So for example, if you have x equals to, you have AU plus BV plus CW. So this U, V, and W are vectors. Okay, whereas this A, B, and C are scalars. Okay, so if you see this example here, x is given, u is given, v and w are all given, and the question here wants you to find the scalar value of a, b, and also c. So this is the step-by-step of what we did in class last week, and we got the answer is a equals to 1, b is negative 2, and c is negative 1. Okay, so and then after that we moved into vector space. So if you still remember vector space, there are 2 main properties that you need to check. The first one is given by this alpha here, which is closed under the addition. So you have closed under addition. And the second one is, which is the B part here, which is closed under scalar multiplication. So you have closed under scalar multiplication. So this is actually the 2 main property that you need to check in order for us to verify that a set given to us is actually a vector space. All right. So if you still remember, under each of this one here, it's divided into another 5 properties that you need to check. All right, so 1, 2, 3, 4, 5, and these 5, if you add these 2 properties here, you're going to have a total of 10 properties. So all these 10 properties here that you need to check for a set. So actually you start with a set given to you. You check if it's a vector space or not by using these 10 properties here. So these 10 properties here are listed in this definition of vector space. So you have all these 10 properties that you need to verify in order for a set to be a vector space. Alright, so we had a look at all these examples here, and I would like to emphasize again from example 1 until example 5. If you notice, the examples here, they only check 2 of the properties. Okay, so all these examples here, they only check 2 properties. So you have to check the remaining 8 properties if it's satisfied or not, in order for that particular set given to you is a vector space or not. Okay, so in these examples here, if you see, they only check the vector addition, is closure under addition, and also closure under scalar multiplication. Alright, so only 2 of these properties are checked. So what you need to do is you need to check by hand the remaining 8 properties. So basically in this one here, only number 1 and also number 6 is checked. Okay, so you need to check this one here and also this one here for each of these examples here. Okay, so this is a good exercise for you. And then this is the second example. So you are given set V. You see, at the beginning, we start with the word set. So once you have checked all the 10 properties, then only this set will be declared as vector space. Okay, so you're given a set, you check 10 properties, and then only you verify if the given set to you is a vector space or not. Right? So if you see this example also, they only verified the addition and the scalar multiplication part. Okay, so this is the addition and this is the scalar multiplication. So what you need to do is you need to check the rest of the 8 properties, right? And then you also have example 3. I think in class last week I did give I did give you all a complete example where we checked all the 10 properties related to an example in matrix. Okay, so please study back that example. Okay, so there is an example given in class the last week on matrices, which I go through all the 10 properties. I've shown you how are you supposed to check all the 10 properties for a set given to you to become a vector space. Right? So make sure you study that example again. And then you also have this example 4 here. So example 4 is on all the real valued continuous function. So in this example again, they only check 2 properties, which is the addition and also the scalar multiplication. So you need to check the rest of the 8 properties. Okay, so the solution is given here, some explanation. And then you move on to example 5. So if you see example 5, I think we did this example on the whiteboard last week. So you have this P2 here. P2 represent all the quadratic equations. Quadratic polynomials. So if you have P3, these are all going to be cubic polynomials. If you have P4, it's a quartic, and so on. Alright, so in this example here, it's only concentrating on P2. Okay, so the best way of solving this kind of question is that when you're given a set P2, you extract out 2 examples from here for you to perform the vector addition and also the scalar multiplication. You see in this example here, they took out Px. So you can just randomly assign A2, A1, A0. It doesn't matter, okay? And then you can also have another one which is Qx. So you have B2, B1 and also B0. So it's now easier for you to check the addition part and also the scalar multiplication part. Okay? So make sure you check the rest of the 8 properties. Alright, so these are these are the solution given to you for this example 5 here. So make sure you study this one. And then, okay, so if you see this part here, verification of each of the 10 vector space axioms is straightforward. That's right. For instance, because the set of real numbers is closed under addition, it follows that A2 plus B2, A1 plus B1, and A0 plus B0 are real numbers. So you have Px plus Qx is given to you by this polynomial here, by this quadratic polynomial here, where you have this part and then x squared plus this part x plus this part here, which is equals to hx, and hx is also inside this set given to you, which is P2. Okay, so hx is also inside P2. So this is actually checking closure under addition. So polynomial hx is in the set P2 because it is a polynomial of degree 2. That's right, you have an x square here. And then P2 is closed under addition. Okay. To verify the commutative axiom of addition, we write like this. So commutative means that P plus Q is equals to Q plus P. So what happens in this process here is that it's just the rearrangement of the coefficients, right? So earlier on you can see that this is A2 plus B2. Okay, and then what happened is that all the A and the B's, they change their position. So once they change their position, you can now collect all the B's and all the A's together. So you can see now, earlier on, you have A at the front. Now you have B at the front. Okay, so this B2, B1 plus B0 is the QX part. And also A2, A1, A0 is the PX part. So from here you can see that the commutative axiom is satisfied, where P plus Q is equals to Q plus P. Alright, so what else we had a look last week? So we had a look at the definition of zero vector. So you know what is zero vector? Zero vector is just, everything is zero, which is known as the zero polynomial in this case. So you can see that zero vector is also inside P2 because you can write 0 x squared plus 0x plus 0. So that one is good. So other axioms can be proved similarly. So the procedure used to verify that P2 is the vector space can be extended to show that Pn with usual operations of polynomial addition and scalar multiplication. So in this example here, they are trying to generalize the concept of P2. So by this one here, if you do the same thing for P3, you will get that P3 is also a vector space. And if you extend the same concept to P4, P5, and so on until Pn, you can see that all of these are vector space because they satisfy the property of a scalar multiplication, and also they satisfy the property of vector addition. All right? And also the zero polynomial is included in that particular polynomial that you are working with. Okay, and then you also have this theorem 1 here. This is property of scalar multiplication. So this is in terms of the zero vector. All right. So you have 0 times v is equals to 0. That's obvious. So a scalar multiplied with zero vector, you will get a 0 as well. So you see there's a difference between the 0 that is bold and the 0 that is not bold. So basically, this 0 that is not bold, it actually represents the scalar part. Okay, whereas the 0 that is bold here represents the vector 0. So the same goes to here. If you see the C is not bold, whereas 0 is bold because 0 is a vector. Okay, so a scalar multiplied with a vector 0 is equals to a 0 vector. Okay, so if CV is equals to 0, then either C is equals to 0 or V is equals to 0. And the last one, number 4, is the negative of the vector. So negative 1, which is the scalar negative 1, multiply with a vector, you will get the negative of the vector. Okay, so we also had a look at this one here, sets that are not vector spaces. So we have seen multiple examples in class last week where we have some of the sets given to you are not vector spaces, right? So sets given to you doesn't satisfy the 10 properties. It doesn't mean that it doesn't satisfy all the 10 properties. You have to actually only find one property that is not satisfied, and it is enough to show that a set is not a vector space. All right. So for example, in this example 6 here, a set of integers is not a vector space because it doesn't satisfy the closed under scalar multiplication, because an integer 1, if you multiply with the scalar half, you will get the answer is half, and half is not an integer, right? And also example 7, you are given a set V equals to R3, and you are given this definition here. You are given that x plus y is given by this definition, and c multiply with the vector is given by this definition here. Okay, so you can see that all these properties a, b, c, d, e are satisfied, but then the problem here is in the problem is in, let me see. Okay, the problem is in property F. Property F doesn't hold. Okay, so we have done this calculation in class last week. You can check. You can also check manually for this one here. If you do the calculation for this using the definition given to you, okay, using this definition given to you, you can see that the left hand side is not equal to the right hand side. Okay, so for that reason, the property F doesn't satisfy. There you go, property F is not valid. Alright, so make sure you do step by step for these examples here and check if all the other properties are satisfied or not. And then you also have this example 8. So in this example here, you are given this set V equals to R. So this R here is actually R to the power of 1. Okay, so you know that if R2, you're going to have, okay, so if R2, you're going to have something like A, comma, B. So if you have R3, you're going to have A, comma, B, comma, C. Alright? And for this one here, if you only have R1, this one implies that you only have one coordinate. Okay, so only you have one number. So this V equals to R here is defined by this operation. So you have U plus V is equals to U minus V. And then the scalar multiplication CU is the normal multiplication. You have C times U. Okay. So the question here wants you to check if this V equals to R under these two definition here is a vector space or not. So if you see that, the property A fails. Okay. Because if you calculate property A I think is commutative. Commutative implies that if you have U plus V, it should be equals to V plus U. But then under this definition here, U plus V is U minus V. Okay, so in this example, we take U equals to 2 and V equals to 3. So if you take U minus V, you will get -1, whereas V minus U on the other way is 1. So -1 is not equals to 1. So for that reason, commutative property is not satisfied. So since 1 out of 10 properties are not satisfied, it is enough to say that V equals to R is not a vector space. Okay, so we stopped there last week. So now let's continue from this week's lecture here. So today is 17th March 2020. Alright, so now we're going to move on with subspaces of vector space. So in many applications in linear algebra, vector spaces occur as subspaces of larger space. So what does this imply? This implies that, let's say you have this big box here. So this is the vector space. So inside vector space here, you're going to have multiple subsets. Okay, for example, this one here, you have subset V, you might also have subset X, and you might also have this subset Z here, and so on, okay? So for instance, the solution set of a homogeneous system of linear equations in n variables is a subspace of Rn. Alright, so this is the definition here. Let V be a vector space. So we have this box here, V, which is a vector space, and W is a non-empty subset of V. Okay, so you see, you start with this definition first. This term is known as subset. So you start with a subset W. Okay, this is known as a subset. But then when you check the properties, it satisfies properties. Then only you can call this W a subspace. Same like before, you start with the word set. You check all the 10 properties. If all the 10 properties are satisfied, then only you call that as vector space. Okay, so now W is known as a non-empty subset of V. So if W is a vector space with respect to the operations in V, then W is called a subspace of V. Okay, so you see, let me explain to you this definition here using this diagram. So we have this vector V. Okay, and this vector V, you already check using the 10 properties that this is a vector space. Okay, you already checked. Okay, and then inside this vector V, vector space V here, there are multiple subsets. Okay, you have subset W, subset X, subset Z, and many other subsets. All right. So now your job is now to check if each of these subset here are subspaces or not, because and in this definition it says that for these subsets here to be subspaces, they must satisfy the same condition satisfied by V. Okay, so for example, this W here, it starts with being a subset, and then you check for, what does it say? W is a vector space with respect to the operations in V. So you have to basically check all the 10 properties. 10 properties with respect to V. And then only if it satisfies, then only you will say that W is also a subspace. Alright? Okay, so let's have a look at one example here. Let W be subset of R3. R3, so you know, R3 is going to be something like A, B, C, for example. Okay? And consisting of all vectors of the form, this one here. So you are given, wait, let me just grab a piece of paper. Where is my paper? Alright, let me just sketch this one here. So you have W, which is a subset of R3. And the form of this W here is given by, you have A, B, 0. Okay, where A and B are any real numbers, right? With usual operations of vector addition and scalar multiplication. Okay, the question wants you to show that subspace W is a vector space. So for this W, now it is known as a subset because we haven't checked the properties yet. So now your responsibility now is to check the properties, because the question wants you to the question wants you to verify if this W here is a subspace or not. This subspace W is a vector space or not. Okay, so now you have to check all the properties. Okay, so in this notes here, if you can see, they only check two of the properties. The first one is the addition, and the second one is the scalar multiplication. So let's say in this example, you're given U, let's say any A1, B1, 0. Remember, the vectors that you choose must correspond to the subset that you are dealing with. And in this question, you already said that W is given in this form, A, B, and then you have the third coordinate is equals to 0. Okay, so let's say you have U equals to A1, B1, 0. And then you have V equals to A2, B2, 0. Okay, so there are two main properties that you need to check. The first one is the addition, and the second one is the scalar multiplication. Okay, so for addition, it's easy. You just have to check if U plus V is also inside W. Okay, so if you check, you will get A1 plus A2, comma, B1 plus B2, comma, 0 plus 0 is back to 0. Okay, so now you see, is this vector here corresponds to the same form given by this W? Yes, it does, because the first coordinate is any real number, and A1 plus A2 is also any real number. The second coordinate is a real number, and B1 plus B2 is also any real number. And the third coordinate is 0. The third coordinate of U plus W is also 0. So this is, yes, indeed inside W. So the addition part is done. Okay, the next thing you need to check is the scalar multiplication. So for scalar multiplication, you can just take any of these, any one of these two vectors here. Let's say I choose V. So you multiply with C. So C scalar multiply with V is equals to C multiply with A2, B2, 0, which is equals to C A2, C B2, and C multiply with 0 is just 0. Okay, so let's check if these two forms are the same. CA2 is any real number, that's good. B is any real number, CB2 is also any real number. The third coordinate 0, 0, yes indeed. Scalar multiplication is also inside W, so all good. Okay, so now what is left to check? You still have to check that the other 8 properties are satisfied. I'm just going to put a question mark here because you have to check manually by yourself, okay? All right, so we can see that thus properties of A and B of definition 1 holds. The verification of the other 8 vector space axioms are left as exercise. So you have to do that, okay? Hence, we can conclude that W is a subspace of R3. Alright, so theorem 1, test for subspace. If W is a non-empty subset, okay, so you have this W here, a non-empty subset. What does non-empty means? Non-empty here means that inside here, there are vectors. It is not empty, alright? So if W is a non-empty subset of a vector space V, then W is a subspace of V if and only if the following closure condition hold. Okay, so if you see these two closure condition here, they are actually going back to the same condition of addition and also the concept of scalar multiplication. Alright, so these are the two properties that you need to check in order for W, which is a subset of vector space V, to be a subspace of V. Right? Okay, so let's see this example here. Let W be set of all 2 by 2 symmetric matrices. So, do you still remember what's the definition for symmetric matrices? So this is example 2. So what does it mean by symmetric matrices? Okay, so let me just have a look. Symmetric matrices. Okay, the definition of symmetric matrices is a square matrix. Do you still remember what's the definition of square matrix? Square matrix means the dimension is the same. Okay, so let's say 2 by 2, 3 by 3, 4 by 4, and so on. Okay, so these are known as square matrices. Okay, so symmetric matrix is a square matrix that is equal to its transpose. So symmetric matrix here means that if you have a matrix A, it is equals to its transpose. The matrix A is equals to its A transpose. So one example of symmetric matrix, what is it? For example, if I take a 2 by 2 matrix, maybe I take 1, 2, 2, 3. Okay, so this is the diagonal line, and you can see this element and this element are the same. Okay, so this is matrix, symmetric matrix. Okay, because the elements of A transpose is equals to the matrix of A. So by the way, what is the A transpose of this? The A transpose means that the column is now going to become a row. So this column 1, 2 is now, sorry, this row 1, 2 is now going to become a column, and this row 2, 3 is going to become 2, 3. So is it the same? A transpose and A? They are the same. Okay, so this is one example of symmetric matrix. Alright, so now that you know the definition, let's go back to the example. So let W be the set of all 2 by 2 symmetric matrices. Show that W is a subspace of the vector space M22 with standard operations of matrix addition and scalar multiplication. Okay, so you are given W, and the question wants you to check if it is a subspace. Subspace of M22 with the standard operation. So there are two things for you to check: the addition and also the scalar multiplication. Alright, so let's have a look at the solution. Okay, recall that a square matrix is symmetric when it is equals to its own transpose. Since M22 is a vector space, we need to show that W, which is a subset of M22, satisfies the conditions of theorem 1. So what is theorem 1? Let me check where is it? Theorem 1, example 1, definition 1. Okay, so where is theorem 1? Okay, theorem 1. Theorem 1 is this one here. Okay, that's for subspace. Alright, so we're going to use these two vector addition and also scalar multiplication to show that this W here is a subspace of this M22. Alright. Okay, so let's see the first one. W is closed under addition because for matrix A1, A2 in W, we have A1 equals to A1 transpose and A2, this is supposed to be A2. There's a typo here. Can you please correct that? A2 is equals to A2 transpose, which implies that, so under addition, you are given A1 equals to A1 transpose, and then you have another matrix, which is A2 equals to A2 transpose. Why are they equals to their transpose? Because the definition says that W is a symmetric matrix. Symmetric matrix. Okay, so now let's check the addition part. So A1 plus A2. A2 transpose. So what does this equal to? Do you still remember the properties for transpose? So if it's addition, the properties of transpose says that A1 is going to be transposed plus with A2 transposed. Okay, so what is A1 transpose from here? A1 transpose is equals to A1. What is A2 transpose? It is equals to A2. So you can see that A1 plus A2 transpose is equals to A1 plus A2. Okay, so you can see that the addition holds, right? So if A1 and A2 are symmetric matrices of order 2, then so is A1 plus A2. Okay, so similarly, W is closed under scalar multiplication because A is equals to A transpose, implies that, okay, so for the scalar multiplication part, let's say you have C, A transpose. Okay, so what is this equals to? What is C transpose? I think I've mentioned this before as well. Let's say you have a number, you transpose it, you're going to still get back the same number because this is scalar. It's different than when you're dealing with matrix, okay? So this scalar C here, if you transpose it, you're still going to get a C. And if this A, you transpose it, you're going to get A transpose, okay? So what is A transpose? You know C is still a C. A transpose is actually, A transpose is going to be equals to the matrix A itself. So this is going to be equals to CA. So from here, you can see that CA transpose is equals to CA. Okay, the